Welcome to qnawire.
Hi everyone, so what we have is a house of volume 400 cubic meters that has an internal pressure of 95 kPa. It is desired that the temperature go from 14 degrees C to 24 degrees C through a heating system. The heating system consists of ducts and a 250 watt fan and a 30 kilowatt heater. And we know that every time this air passes through this duct, the temperature raises by 5 degrees C. We know the house is losing heat at a transfer rate of 450 kilojoules per minute, and what we're asked to solve for is the time it takes to heat this house up to 24 degrees Celsius and the mass flow rate of air through this duct system. So what we're going to assume first is that we're operating at steady state conditions, so properties will not be changing with time. We're also going to assume that air is an ideal gas. Next, we're going to assume that any changes in kinetic energy and potential energies are negligible. Now what we're going to do is go ahead and write down the properties of our air. So we can say that since we are dealing with air and it's an ideal gas, we can say that R is equal to 0.287 kilojoules per kilogram Kelvin. We can say that the specific heats of air, Cp, is equal to 1.005 kilojoules per kilogram Kelvin, and our CV is equal to 0.718 kilojoules per kilogram Kelvin. The first thing we're going to do is calculate the total mass of air that's in our building. So we can say that M is equal to P1 V1 over RT1, and this gives us an initial mass in the building equal to 461.3 kilograms. Now we're going to take the entire system, or the entire building, as our system for our energy balance. So what we can do is we can say that the total energy entering is equal to the total energy leaving because we're operating at steady state conditions. So we can break these down by saying that the energy coming in is the work from the electrical heating system plus the work of the fan minus the heat that's leaving the house, and that's going to be equal to the change in internal energy. And we can go further to say that this is going to be equal to the time it takes for which all of these processes to occur times the rate at which electrical power is being used plus the rate at which the fan is absorbing power minus the rate at which heat is transferred. And this will be equal to mCv T2 minus T1. Now we can just directly solve for dt, or delta T, and we can see that delta T will just be equal to mCv T2 minus T1 all over We dot plus Wf dot minus Q dot. And plugging in all the quantities that we know, we get a delta T equal to 146 seconds. So that is one part of our final answer. Next, we're also asked to solve for the mass flow rate of air through the heating duct. So now we're going to take the heating duct as our system. And again, we can say that the rate of energy coming in is equal to the rate of energy leaving the heating duct. And we can go ahead and further break these down into its constituents and say that the work or the power used by electrical fan plus the power or the electrical heating system plus the power used by the fan plus the enthalpy of the air coming through the duct is equal to the total enthalpy of the air leaving the duct. Now we can go ahead and directly solve for m dot by saying that m dot is equal to We plus W dot fan all over Cp times the change in temperature, because we're just using the definition of H equals Cp times T. So by going ahead and plugging in for these quantities, we get a final mass flow rate through the duct equal to 6.02 kilograms per second, and that's our mass flow rate. That's our final answer.